1. That was the goal. Were we able to meet it? Kind of, sort of, right? We found out that there's going to be some locations that will not have anything hashing to them. Some locations will have multiple things hashed to them, some exactly one. We're going to get collisions. How about if we make the packing density lower? We're going to have fewer collisions, but we're going to have collisions. We're always going to have collisions. So we cannot totally get rid of collisions, so we're going to try to do what? To minimize them. Remember I told you I had this Poisson distribution, I fixed that, so actually I have a nice slides that make it clear, but I'm not going to go over that right now. But the other possibility, so there's no guarantee when you're talking about hashing that you're going to get a great performance, although from experience we can get great performance from hashing. Okay? But hashing doesn't always give us what we want. For example, if we want to access the data, very large file, in sequence, we can't do that with hashing. Because hashing just gives you one location, randomly, right? Hashes to different places. So if we want to get things all together, we can't do that. So what we're going to do is we're going to look at indexes. And the idea of an index is something like this. So if this is going to be an index, and this is going to be a large file, for instance, then basically what we'll do is we'll maintain the index, and so this will be the key will be here, and then we'll have a location within the file. So for example, this tells us that the index says the key is the smallest here, but the location is here in the file. This is the next smallest one, and it's actually right here. So you can see that the location of the data on the file could be anywhere, but in the index they're next to each other. So this allows me to access the data in sequence. Okay? But from a computer standpoint, it's actually extremely inefficient. And the reason it's inefficient is because let's say I had 10 million 10 million records, which means I have 10 million keys. Now suppose that each record was 1K. How big is the file? What's 10 million times 1,000? 10 billion. So the file is approximately 10 GB. Big file. So let's say I wanted to print this data in order. If I want to print this data in order, I have to load this into memory, which is 10 million keys. I can probably do that. Big array, but not too bad. And then what I have to do is I have to find here, and I have to do a seek operation. So this is always going to be a seek. This is going to be a seek. In fact, I'm going to perform a seek in the file 10 million times. Well, the question is how long does it take to seek? Well, the answer to that question is that when you're seeking into a file, and it's a large file, it's going to be on a magnetic hard disk drive, which is spinning around. So basically, by the time you figure out where you want it, the data is on this part of the disk, and it's going to spin over. You have to wait for it. It's called rotational delay. On average, you're going to be about half the distance from it. Sometimes it's going to be right here. You've got to spin all the way around. Sometimes it's right here. It's going to get it right away. So it's going to take you half a revolution, which can take on the order of 3, 4, 5 milliseconds. You're also going to have to, the file is very big, you might have to move on the disk. Remember, it's a disk, multiple layers of disks, right, spinning around. You're going to have to move the read-write head to read the data from this track to this track to this track to this track. That's called a seek. That's actually called seek, not to be confused with this generic seek. So you're going to have to seek, you're going to have to wait for the rotational delay. Roughly speaking, let's say each seek, is going to take is going to cost us 10 milliseconds. 10 milliseconds. Then we're going to have to do this 10 million times. So it's going to be 10 times 10 to the 6th, which is 10 million. 1 millisecond is 10 to the what? Minus 1 millisecond minus 3. So 10 of them is going to be minus 2. 10 milliseconds is 1/100th. Okay, so 10 to the 6th times 10 to the minus second is going to be what? 10 times 10 to the 4th, which is equal to 10 to the 5th. 10 to the 5th what? So 10 to the 5th is what, 100,000? All right? So 100,000. And that's what units? What units is that? Seconds, right? So if we divide it by 60. 27.7 hours. What do you think? Can we wait that long? I don't think so. Not very good, right? So we don't like that. Now, let's see. The good news is that it's pretty fast to just get one. If you just need to get one of them, it's just going to cost you 10 milliseconds. But if you want them all, it's going to cost you 27 hours. That's bad. Now, what happens if the file is increased to the point where the index cannot fit into memory? Okay, so we're going to look at, as soon as I get my stuff from my video display. I'll see if you found it. Did you find it?
No.
You didn't find it?
No.
Really?
I had taken all classes, like calculus.
But which class did you go to?
Like downstairs, calculus, and upstairs, maths class, and then.
Math class, no.
No, like this one class. It's like except and it's
Yeah.
it's your class, right?
Yeah.
One more class, yeah.
It's the small room, right?
Yeah.
Was there a class in there?
Yeah.
There was a class? And did you check in the, it should be plugged into one of these things,
Okay.
right? It would have been plugged, probably left plugged in there.
One more time.
Well, by the time you get back, that's never happened to me. It's one of these adapters that doesn't have, you can't, nobody has it. It's a bizarre one. I don't know, maybe. Very strange. No, I did know I definitely used it in that classroom. And it's not this one, not even close. And it's not this one either.